Euler's formula. This is a formula which encompasses some of the most interesting and complex numbers in mathematics. E is Euler's number, an irrational number of which we do not know the exact value, and one which we will be exploring in the video. I is the imaginary unit, a number which when squared equals -1. And pi. This is a ratio of a circle's circumference to its diameter. Throughout this video, I will be discussing who discovered the formula, how they discovered it, and what that means for us. Leonhard Euler was a mathematician and physicist from Switzerland who lived in the 18th century. He made many important discoveries and introduced much of modern mathematical notation and terminology. However, in this video, I will be focusing on one of the works he is most renowned for, Euler's formula. So, what is it? Well, E to the power of the imaginary unit times pi plus 1 is equal to 0. But this is just a special case of a much more useful formula that Euler discovered. E to the power of I times theta is equal to the cosine of theta plus I times the sine of theta. And if we calculate this for theta is equal to pi, we get E to the power of I pi is equal to the cosine of pi plus I times the sine of pi, which simplifies to equal -1 plus the imaginary unit times 0, because the cosine of pi is -1 and the sine of pi is 0. And this further simplifies to equal -1 and can be rearranged so that E to the power of I times pi plus 1 is equal to 0. And although it may seem daunting and baffling at first, it really just describes two equivalent ways to move in a circle. But something to remember is that the units are not in degrees, but in radians. So how could this have been discovered? The concept of imaginary numbers was an area of math which was very interesting to people in Euler's time. So Euler decided to insert the imaginary unit into a Taylor series. Taylor series is an expansion of a function into an infinite number of terms, which can be written as sigma notation. And so he put the imaginary unit in and simplified it, and the terms at the end seemed to prove some sort of miracle. The first group of brackets displayed the Taylor series for cosine, and the second displayed the Taylor series for sine. Hence, the equation E to the power of the imaginary unit times theta is equal to the cosine of theta plus the imaginary unit times the sine of theta. We can see how this shows the movement around a circle by substituting a value in. So if we let x of theta equal 3, it leads us to E to the power of 3 times the imaginary unit is equal to the cosine of 3 plus the imaginary unit times the sine of 3, which when calculated comes to -0.990 plus 0.141 times the imaginary unit to 3 decimal places. The answer is a combination of real and an imaginary number, which together is called a complex number. And we can plot this on a graph called a complex plane, where the real numbers go left to right along the x-axis, and the imaginary numbers go up and down along the y-axis. And here, on this graph, we can see E to the power of 3 times the imaginary unit. Actually, putting Euler's formula on that graph produces a circle. E to the power of I times theta produces a circle with a radius of 1. And we can turn any point into Re to the power of I theta form by Cartesian to polar conversion. This is very simple and can be done using Pythagoras' theorem to find R, the hypotenuse of the triangle, and using the tangent function to find the angle. And if we do this with a number 3 plus 4i, we get that r is equal to 5 and x, or theta, is equal to 0.927 to 3 decimal places. So 3 plus 4i can also be 5e to the power of 0.927i, and this can be seen on the graph. There are many cases where it is easier to use the form re to the power of I theta than a plus bi, for example, multiplication. So the two different methods are very useful. So that's it. This beautiful equation is just about spinning round in circles. It gives us two formulas to explain circular motion and is a clever way to merge the x and y coordinates into a single number and plot the imaginary numbers along the opposite axis. The concept of combining the x and y coordinates into a complex number is hard but manageable. But the imaginary growth is a very difficult concept to grasp. A good description is it's like a jet engine that was strapped on sideways, and instead of going forward, we start pushing at 90 degrees. The clever thing about this perpendicular push is that it doesn't speed you up or slow you down. Instead, it rotates you. So you can take any number and multiply it by I, and it will not change its magnitude, only the direction it's travelling in. Surprisingly, this imaginary growth does not change the length. It's hard to see because it appears to make a triangle where the hypotenuse is getting larger, but the continuous perpendicular growth will simply rotate you, nothing else. This distance around the circle is an angle in radians, showing that we've found another way to describe circular motion. So we have real and imaginary growth at the same time. The real numbers scale us up, and the imaginary ones rotate us around. This is complex growth. But why would this be useful? We could already describe the motion in a circle as sine and cosine. Why is it special? But the sine and cosine describe motion in terms of a grid, plotting horizontal and vertical coordinates, whereas Euler's formula uses polar coordinates, showing the angle and the distance. Again, it may just be two different ways to describe the same motion, but this flexibility is very handy. Depending on the problem, polar or rectangular coordinates may be more useful than the other. And Euler's formula lets us convert between the two to use the best one for the job. And on top of this, because e to the power of I theta can be converted to sine and cosine, we can rewrite formulas in trigonometry as variations of e. This is once again another very useful task Euler's formula lets us carry out. The most stunning thing about this concept is that every number in the world, both real and complex, is a variation of e.